Hello, welcome back. Last time we were together, we learned a couple tests for divergence and or convergence of series. We learned the nth term test for divergence, we learned the geometric series test, and we learned the integral test. So we're going to continue on and we're going to learn today about a p-series test and a couple of comparison tests. A series in the form of okay, so the infinite sum of 1 over n to the p. Now that's a little bit different. N is changing. That's the base that's changing. But the exponent here is just a positive constant, just stays the same. So this is called a p-series. Specifically for p equals 1, that has a special name called the harmonic series. Now, a p-series converges if p is greater than 1, and the series diverges if p is between 0 and 1, including 1. The series diverges if p equals 1, and I say that separately because this is that special one called the harmonic series. So let's practice that. Do the following series converge or diverge? Now we have n in the base, and we have this positive constant 3 as the exponent. So p equals 3, which is greater than 1, so the series converges. Isn't that easy? What about b? 1 over the square root of n. Well, that's n to the 1/2. P equals 1/2. That's less than 1. So the series diverges. Woohoo! It's easy to get confused between a p-series and a geometric series, and let me show you why. And I think it'll be helpful to see these side by side. So a p-series, that's the one we're just learning right now. It diverges if p is between 0 and 1, and it converges if p is greater than 1. Now, a geometric series, this is the one we learned last time, it diverges when you're greater than or equal to 1 and converges if you're less than 1. So, it's backwards. So it's important to recognize that those are different. In a p-series, n is on the base, and in a geometric series, n is in the exponent. So it might take some practice to get those straight. Example 2. For what values of k will this series converge? Okay, we have what's setting itself up to be a p-series. We have n in the base, and then we have 2k minus 5 as the exponent down there in the denominator of the fraction. So if this is a p-series and we want it to converge, then that exponent has to be greater than 1. Well, now we just have to solve for k. So as long as k is greater than 3, that series will converge. B. Well, it doesn't look like a p-series right now, but if we go ahead and multiply that n through, then we get 1 over n to the, 2k plus 1. Now, if we want it to converge, that 2k plus 1 has to be greater than 1. So anytime k is greater than 0, we have a convergent series. Oh my. Now, what do you do with this one? So it kind of, actually, it doesn't look anything like a p-series right now, but it actually could be. Now, a p-series has like a 1 on the top usually. Well, how do we make that n into a 1? We could divide it by n. Well, if we divide the top by n, we have to divide the bottom by n also. So n over n is just 1. So let's rewrite that again. And then as n is going to infinity, this 5 over n becomes a 0. And now, look at what we have. Now we have a p-series, and if we want it to converge, then that 4k minus 1 has to be greater than 1. So k would be greater than 1/2. That's it for p-series. Now I'm going to show you two comparison tests. One is this one, the direct comparison test for convergence. And this one says, let a sub n be between 0 and b sub n for all n. Then, if the infinite series of b sub n converges, then the infinite series of a sub n also converges. If the infinite series of a sub n diverges, then the infinite series of b sub n also diverges. Now, why is that? It's important to know which function or which series is bigger than the other, because if b sub n converges for all n, that means that a sub n gets squeezed into converging. If a sub n diverges, then b sub n gets pushed into diverging. Example 3, determine if the following converge or diverge. Okay, this is not a p-series because n isn't the base, but this, like if it was just this one, 1 over 2 to the n, I could figure that out because that is a geometric series. So that's what I'm going to choose to compare it to, 1 over 2 to the n. Now, what I know is that 1 over 3 plus 2 to the n is smaller than 1 over 2 to the n, because on the bottom of this fraction is a bigger number, which makes the whole fraction a smaller number. I know that 1 over 2 to the n, that's a geometric series, with a common ratio of less than 1, so it converges, which means, whoops, let me clean this up, which means my original series gets squeezed into converging. So my series here converges by the direct comparison test. Let's try another one. 1 over 4 to the n minus 3. Okay, now stop taking notes for just a sec and watch. I could compare that to 1 over 4 to the n. Again, that's a geometric series. Now this time, 1 over 4 to the n, that's less than 1 over 4 to the n minus 3, because the denominator this time is smaller, so the number is bigger. Okay, so I know that this geometric series has an r less than 1 and it converges. Well, that actually doesn't help me with this one. I can't make a conclusion based on that information. So could I compare it to something else? All right, now you can start taking notes again. Let's compare it to 1 over 3 to the n. If I compare it to 1 over 3 to the n, now my original series here is less than 1 over 3 to the n, because the bottom is bigger, because that 4 to the n makes it bigger. So, the number is smaller. Now I know that 1 over 3 to the n is the geometric series that converges. And so my original series here gets squeezed into converging and converges by the direct comparison test. Okay, C. If you were to compare this to something, what would you compare it to? Let's compare it to 1 over n squared. So if we compare it to 1 over n squared, is this bigger or smaller than 1 over n squared? It's smaller. 1 over n squared is a p-series. P is greater than 1. That series converges, and so our series converges also by the direct comparison test. We're going to switch gears here and talk about the limit comparison test for convergence. This one's awesome because you don't have to worry about what's bigger and what's smaller. What it says is, if a sub n is positive and b sub n is positive, and the limit as n approaches infinity of a sub n over b sub n equals L, that's where L is, it's a number, a finite and positive number, then the infinite series of a sub n and the infinite series of b sub n either both converge or both diverge, which probably sounds like a lot of gobbledygook so far. But again, it's awesome because it doesn't matter which one's bigger. Now, for the sake of consistency, we're going to say that the denominator is what we're comparing it to. This is a comparison test. So we're going to find a comparison series again. And just for the sake of consistency, we're always going to put that in the denominator. Determine if the following series converge or diverge. Now, this is a very complicated looking series. And if I used the direct comparison test, it would just be really hard to figure out if this one is bigger or smaller than a certain thing I compare it to. So instead, I'll show you the limit comparison test. Now, the leading terms of this a sub n are 2n squared over 5n squared. So that's what I could compare it to. But actually, I can just simplify that and just go 2 over 5n cubed. But we're going to infinity, so 2/5 is not really going to matter much. So let's just compare it to 1 over n cubed. This is a p series, and it converges because p is greater than 1. This is what we're going to divide by, this whole thing. Now, if you divide by a fraction, that's multiplying by the reciprocal. So let's write this out. We have our original series, and we're dividing it by what we're comparing it to. But actually, we're multiplying by the reciprocal. And if we clean this up a bit and distribute that n cubed through, we can really see what's going on. The limit as n approaches infinity of this whole thing is 2/5. That's a number. So because what we compared it to converges, then our original one also converges by the limit comparison test. Let's try another one. Again, it's kind of complicated, but we can compare it to something maybe not quite so complicated, like 1 over 5n squared, or just 1 over n squared. This is another p series. It converges because we have a p greater than 1. So we're going to flip and multiply. And we could just see here, we've got our leading terms of n squared and 5n squared on the bottom. So as n approaches infinity, this limit goes to 1/5. That's just a regular positive finite number, which means because our comparison series converged, our original series also converges by the limit comparison test. You starting to get the hang of this just a little? They really do take practice. Oh dear, now we have a radical, but that's okay. The leading terms are basically 1 over the square root of 3n. So we could compare it to 1 over the square root of 3n, or perhaps just 1 over the square root of n. That's another p series, but it diverges because p is 1/2. Okay, so now we just get to flip and multiply and see what we get. The limit as n approaches infinity on this one is 1 over the square root of 3. It's a number, so because our comparison diverged, our original also diverges by the limit comparison test. Ew. What the heck do we do with this one? Like, there's so much going on. So what could we compare this to? Let's take the leading terms and see what we can do. We could compare it to 3 to the n over 4n squared, because this top n kind of gets sucked into the bottom there. Or just 3 to the n over n squared. But what do we do with that? This is where I think convergence and divergence really gets hard, because you have this whole toolbox of different tests to use, and we're going to pull one out that we learned last time. If you take the limit as n approaches infinity of this, you don't get 0. So this guy here diverges by the nth term test. Remember that from last time? So if we've got that down, now we can flip and multiply. And then this one's kind of fun because you can start canceling some stuff out. The 3 to the n's are gone. And then we've got an n and an n squared there. So we have a limit of 1/4. That's the number. Finite positive number. Therefore, since our comparison diverged, then our original also diverges by the limit comparison test. Pause the video if you would, and just try this one on your own. See if you can come up with what to compare it to, if what you compare it to converges or diverges, and then what that means for our original series. How did you do? I'm comparing this to n over n to the 3/2, or just 1 over n to the 1/2. That diverges. It's a p-series with a p less than 1, so I can flip and multiply. I can clean it up a little bit so I can see what's going on, and I have a limit of 1. That's a number. Since my comparison diverged, my original also diverges by the limit comparison test. And we will stop there for today. We still have some more tests to learn, but it's important to practice these for a while. Get good at these, and then we can learn some of the next ones. I will see you next time.